Ugh. I'm dying. It's at 9 p.m. I just woke up and remembered, oh snap, I have a project to do. And so here we are, doing this project last second. You didn't see that. On its own, just a proton and an electron. However, once it gains a positive charge and the electron goes away, it leaves just a proton. Nothing else, just a proton. However, losing an electron isn't the only way for ions to bond or like form or whatever the proper word is. It can also gain an electron, and that forms the hydride ion. Helium likes to share its electrons through covalent bonds and really likes to bond with its homie boron. It like does like a whole whoop 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 like net kind of thing, you know what I'm saying? It's like a diamond. Next is the alkali metals. Every single one of these is going to have an oxidation of +1, and the reactivity of the group is going to increase as you go down, with the most reactive atom actually being inside of this group. And lithium specifically is kind of weird because it likes to act more like magnesium than a normal alkali metal. Lithium also has a charge to radius ratio that is similar to magnesium. So I guess it just doesn't like alkali metals. The other crazy thing about the alkali metals is that it's kind of got some copycats with NH4 and thallium, both acting a lot like the alkali metals. Group 4A. These guys are interesting because they can either gain these four more electrons or just lose these 4. These guys prefer more covalent bonds than ionic, with carbon being in here, which is the basis of all of organic chemistry. Carbon forms chain-like molecules, which is called a word that I don't know. Next is the alkaline earth metals. These guys all have a +2 oxidation number because they'd rather give up those 2 and have an empty second shell to get to their 2 electron valence shell. Beryllium is used for things like non-sparking tools. Magnesium acts weird again, being significantly lighter than aluminum, despite aluminum being in the next group over. Next being group 3A, which contains elements like boron and aluminum. These guys have a +3 oxidation because it's easier for them to get rid of these 3 electrons than it is for them to gain 5. Not much weird with this group, just that. Phosphorus is too big for me to make out of popcorn. So just imagine this looks like phosphorus. But phosphorus comes in 3 forms: red, white, and black. It's also used in fertilizers. Red phosphorus is used in things like matches. White phosphorus is a war crime. And I don't know what black phosphorus is. Group 5A goes back to just choosing 1 oxidation charge, which is -3. This group also contains the atom nitrogen, which is in goddamn everything. It's in explosives, it's in fertilizer, it's in our atmosphere. It kind of just doesn't like to be held down. This one right here is oxygen's group, also known as the chalcogens. Their most common oxidation number is +2, because they have 6 electrons. They're basically almost there. Oxygen is in this group. This is it right here, actually. It is the most plentiful element in the Earth's crust. 7A, halogens. Halogen is probably Latin or something for salt forming. These elements are very reactive. with this right here actually being the most reactive of the halogens, because they become more and more reactive as they get smaller, because the positive charge in the nucleus makes it easier for it to suck in more electrons. I need more popcorn right now.
Take it.
Okay. These elements specifically like to react with the alkali metals because it's just such an easy bond. You know, 7 valence shell electrons and 1 valence shell electron. Match made in heaven. Almost done. We have the noble gases. This one right here being, I want to say, neon. These gases having a full 8 electrons in their valence shell, except for helium, which only has 2. They are very unreactive. However, that doesn't mean that they don't react at all. Fluorides of xenon and krypton have been produced, which means that they have bond with fluoride, or fluorine, sorry. And finally, we have transition metals. Now, I don't really know how to make the transition metals. So, instead, while I clean up a little bit, I'll continue telling you their properties. The transition metals is that big chunk of metals, or elements, I guess, in the middle, just right there. It'll be lower than all of them. It'll go whoop, 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 and then that whole box, those are transition metals. It's got elements like chromium, which is really good at resisting corrosion because of its stable electron configuration. I wish I could show you, but I'm running low on popcorn. With this, chrome is used for stainless steel, along with resisting corrosion. Zinc is used as a coating to protect iron from rusting through a process called galvanization. Now, that concludes this. Please, I'm so tired. It's not that late. I just don't want to fail.